now we see some more definitions. Okay, we are not going to prove any theorem in this part, but we are going to see more notations and definitions and some results also. The last result would be a general version of Feynman-Cauchy formula that we are going to prove in another lecture. Okay, so consider the SDA dxs bsxs ds plus sigma sxs dws for all s greater or equals to t, and xt is equal to small x. This is not a new SD. We have seen some this type of SDs before, but only thing is that every time when we wrote SDs, we have written all the time s is greater or equals to 0. Okay, but here that we are writing s is greater or equals to t, so that means t is a particular positive time and a particular member in the space, and then at that time, at that position x, we now start looking at the evolution of the SD. Okay, and if we consider such type of SDs which is not starting from origin, not starting from 0 time, but initial time is a different time t. Okay, so we would like to often denote the solution using this t comma x also. Okay, so we would often like to carry this notation tx there. Okay, here b and sigma assumed to be continuous and has at most linear growth, all these condition as before, and then this equation, this one has a weak solution for every pair tx. Okay, so the proof of this would be exactly as before. Okay, so weak solution, and then this solution is weakly unique, and we are going to denote this solution as x superscript t comma x s, and s is greater or equals to t. The operator A is called elliptic. Okay, this is another definition of some classes of operators. An operator A is called elliptic if at each and every x aij x sigma is xi I xi j. Okay, so this is nothing but the quadratic form, correct? So xi transpose a xi, okay, that is written in terms of double summation. Okay, so here yes, there is a typo, it should be j is equal to 1 to d, d. Aij x sigma xi I xi j greater than 0 for all xi in Rd minus 0. Okay, of course xi, when xi is origin, of course this is 0. I mean, there's nothing big deal, but when xi is non-zero, then this is non-zero. Okay, this is a strong condition on the coefficient A, and if that condition is true, then the operator A is called elliptic. We call A as uniformly elliptic in a domain D, which is open domain D. So this is like open subset of Rd. If there exists one positive delta such that the same quantity aij x xi I xi j is greater or equals to delta times norm xi square. Okay, this is a stronger condition. Okay, doesn't matter what x is in D. Okay, so for all x in D it is true. This implies this, but the reverse is not true, correct? Okay, so now what is the Dirichlet problem in this general setting? Remember, we have discussed Dirichlet problem earlier also. We have spent quite some lectures on that, about the solution of the Dirichlet problem, and then when can you assure existence of solution. So for the sufficient condition, we looked at the regularity property of the boundary of the domain. So here what we do is that again we are revisiting Dirichlet problem, because there in that Dirichlet problem only Laplacian operator we have considered. Since Laplacian operator is associated with half times Laplacian is associated with Brownian motion, so only Brownian motion was used to study those problems. And that connection is clear from here, because this Laplacian and Brownian motion are connected, correct? Because this is a solution of Brownian motion is the martingale solution for the half times Laplacian operator. However, here what we are going to do is that we are going to look at a different, more general equation where the operator A would appear, that would have maybe variable coefficients, okay, and that may also have first order term. Okay, so AU minus KU is equal to minus G in the domain D, and on the boundary it is having some boundary data that U on the boundary of D is equal to F. So we ask that what is the solution of this equation? Find U, which is constants on the closure of the domain and twice differentiable inside the domain, such that this is true. Where these Kg are given this way, that so here this is G, this is a typo, is not theta. So K is a non-negative function defined on the whole closure, and G is a real valued function defined on the whole closure of D, and F is defined on the boundary of the domain. Okay, so this is a real valued function, and all these functions are assumed to be continuous. So that is the settings what we are going to discuss. Okay, so I am not going to give a proof of existence of this, but I am just stating this result, that let U be a solution. So here we are not asserting anything about the existence. I mean, we are assuming that if it exists, okay, that let U be a solution to the above Dirichlet problem. Then we are going to write down the solution in terms of conditional expectation, okay, of functionals of the process X which solves the SD. Okay, here in this case maybe FSD. Here this A is coming from the SD part, so where we do not have the parameters depending on the whole path functional, but only at the position of the path. Okay, so that is my A. So to distinguish between this A and A prime, I use these two notations. So this X is coming from that SD. So then the solution would be written in this manner, where tau D is first exit time from the domain D. So here it is written this way, and we also assume that that conditional expectation of tau D is finite for any starting point X from domain D. So under those assumptions, the solution of the Dirichlet problem U of X can be written as conditional expectation of f of tau X tau D times e to the power of minus 0 to tau D K of xs ds plus integration 0 to tau D G of xt times e to the power of minus 0 to t k xs ds dt. Okay, so here t is running from 0 to tau D, and here s is running from 0 to tau D, and here s is running from 0 to t. Okay, given x0 is equal to x for all x in the D closure. So that defines a function on the D closure. So all these things are well defined because of this property. I mean, this is essential thing to assume, because if tau D is not finite valued, I mean expectation is not finite valued, then we might not be able to do much. Okay, actually tau D should be first finite valued. Okay, and then this is little extra condition than that expectation is also finite. Okay, so if tau D is not finite valued, of course one cannot write down these things, correct, because then x infinity makes no sense. Okay, now we write down a sufficient condition for this thing. There is a typo, this is tau subscript D. Sufficient condition for expectation of tau subscript D given x0 is equal to x is less than infinity. So this expectation is finite. When can it happen? So one would ask that, okay, can I find out any condition on the coefficients of the SD under which this can be assured? Yes, that can be, but of course the domain also plays an important role. So here ALLX, okay, and you run over all possible x and take the minimum. Okay, if the minimum of ALLX for all x in D closure, so minimum of ALLX on the D closure set, if that minimum is positive, okay, and this is true for some, okay, L in 1 to D, that would imply that expectation of tau D, so here it is correct, so expression of tau D is finite. Okay, so now I state another result. So here I have stated this result for Dirichlet problem without a proof. Now here we are stating another problem, the Cauchy problem, okay, in this more general setting where it is not only coming from the Laplacian but the variable coefficient general second order elliptic operator. So here let f, g, k are continuous. These are exactly having the same meaning, like g is Lagrangian, k is potential, and f is terminal condition, and then these are at most polynomial growth. F has at most polynomial growth. Okay, so here 2 lambda, correct? So polynomial degree 2 lambda. And g is also at most polynomial growth. So either this condition one can choose, alternatively one can choose that, okay, both are non-negative. Okay, so for the sake of statement, let us just concentrate on that. I mean, let us just read this part. So mod f and mod g are at most linear, at most polynomial growth, and then we can assert the following. What is this? This is saying that suppose v is a continuous function, okay, on the function of time and space and are devalued. Okay, there is a typo here. It should not be RD, it should be R only. There should not D here, because v is a real valued function. So v is a real valued function, okay, continuous function, and once continuous differentiable with time and twice continuous differentiable with space, and solves del v del t plus atv plus g is equal to kv, this k, okay. So see here I am not writing the details, like g is also function of t comma x, k of t comma x, v of t comma x, but that is understood. So this is true in the domain that close 0 to open t Rd, and the terminal time Vtx is equal to f of x, and this has at most polynomial growth, the solution. Okay, so we here suppose that this Cauchy problem, del v del t plus atv plus g is equal to kv, has one classical solution with at most polynomial growth, that mod of v is less than or equal to m times 1 plus mod x to mu. So this is the polynomial degree, okay, for some capital M greater than 0 and mu greater than or equal to 1. Then we can write down the solution v in terms of conditional expectation. Then for all t comma x in 0 to capital T cross Rd, Vtx is given by this formula. V of tx is equal to expectation of f of x capital T e to the power of minus small t to capital T, k of u x u du plus integration small t to capital T g of s xs into e to the power of minus small t to s k u x u du, and the integration of this to s ds is s is running from small t to capital T here, given xt is equal to small x. Here we are going to see its proof in the next lecture. So a few things are pretty much clear here. When we write down, say, small t is close to capital T, so then say small t is equal to capital T, if you put here to e to the power of minus 0, correct, because this is integration capital T to capital T, so that would be 1, and then here this integration will vanish, so it will be f of x capital T given x of capital T is equal to x, that is f of x itself, so you would get this thermal condition to be true. Okay, if you remember that when we have stated Fehrenbach formula, we did not have x as a solution of SD, but we had Brownian motion itself here. Why? Because there the operator was just half Laplacian here. Okay, since it was just half Laplacian, only we have taken the Brownian motion, but here it is a general variable coefficient second order elliptic operator. So we are looking at the solution of the SD. Okay, so that solution we are picking up here to write down the solution of this equation. So this equation is written as expectation of the function of the solution of the SD, okay, where the coefficient of the SDs do appear in this operator. Okay, so this is the statement of general version of Fehrenbach theorem. Okay, thank you very much.